All right, guys, it's 10 o'clock. Thank you guys for being here. If someone would unmute and let me know that you can hear me and see my screen, I would appreciate it.
Yes.
All right, I didn't hear anybody, so please give me a notice.
Yes. We can hear you.
All right, let's see. I'm not hearing you. All right, try again, please, Shania.
We can hear you.
Okay, good. Thank you. So, please keep your mics muted during the session. Unless you have a question, then feel free to unmute and ask it. We want you to ask questions if you have them. Google Meet sometimes is a little finicky, and if there are a lot of people with mics on, you get a lot of background noise. And if there are a lot of people with webcams on, it slows down the process. So just keep those off. If you have a question, like I said, turn them on. Feel free to ask. We want you to ask. We are recording this session, and the recorded version of the session will be posted to the A+ College Ready Science YouTube channel. If you haven't checked out that YouTube channel, there's all kinds of videos there that could really help you with AP Physics 1. So just search for you got to spell out plus College Ready Science YouTube channel. Week 6 version of this next week will be held same time, same place. So Friday, October 2nd at 10 a.m. Today we're talking about forces, specifically dynamics. So in the first unit of AP Physics 1, you dealt with this, kinematics. So this is the branch of mechanics that looks at the motion of objects, but doesn't go into detail of the forces that make the objects move. What we're talking about in the second unit in the course is dynamics. So dynamics is the branch of mechanics or physics that's concerned with forces and also torques, and how those forces and torques affect motion, how they make things move, how they make things accelerate, for example. So a force is a really important idea in this unit. A force is really simply just a push or a pull, but it's a push or a pull that changes the state of rest or uniform motion of an object. It makes things move, or it makes them change how they are moving, whether that's in the direction or maybe the shape of the object or the rate at which the object is moving. Typically in physics, we're going to measure forces in newtons. That's the SI unit. If you're working with the old English system, you could use pounds to measure force. We are very rarely going to use pounds in physics. We're going to stick with newtons. And we're going to talk more about what a newton is here in the next couple of slides. So really important in this unit are Newton's laws of motion. I know you've been hearing about those since probably the first or second grade. We're going to go into a lot more detail with them in this class, really specifically Newton's second law. I'm going to tell you, this is probably the most important idea in all of AP Physics 1. You are going to use this nearly every day from here on out in this class. Really, the only unit that it won't be important in is the electricity unit. Other than that, Newton's second law is going to show up everywhere. It's really important to understand Newton's second law. Again, more about that in a second. The first law is the law of inertia. Remember that inertia is a property of matter by which it continues in its state, whether it's not moving or whether it is moving, and it's going to continue in that state unless it's acted on by some kind of outside force, which we're going to call an external force. And we're going to be more specific and say an external net force. So mass is really just another way to measure how much inertia an object has. Something with more mass is harder to change how that object is moving. It takes more force to change that object's movement. So that's Newton's first law. And you guys know it's usually stated an object in motion will remain in motion unless acted on by a net external force. Let's focus on Newton's second law for a minute. This is really Newton's second law. Net force equals mass times acceleration. we might rewrite it as acceleration equals net force divided by mass. So net forces cause acceleration. More net force means a bigger acceleration. More mass means a smaller acceleration. So mass and acceleration are inversely proportional. Mass and net force and acceleration are directly proportional. So let's look at the equation for a second for Newton's second law. And this will let us derive what a Newton is. So here's force. This is going to be measured in newtons. Mass we know is measured in kilograms. And acceleration is usually measured in meters per second square. So that unit, a kilogram times a meter over a second square, that is a Newton. So 1 Newton is 1 kilogram times a meter over a second square. That's an important fact to know because it's going to help you when you're canceling out units doing calculations. And one of the best ways to check your answers is to make sure that you have the right units. If your units are right and they make sense, there's a good chance that the rest of your math is right too. So net force is a key idea. For example, let's say that we had an object that was acted on by 4 different forces. So let's say there was an object pulling it down, let's say 20 newtons. Let's say there's an object pushing it up, let's say 20 newtons. Let's say there's an object pulling it toward the right, let's say 40 newtons of force going that way. And let's say an object, a force going this way to the left, we'll say at 30 newtons. And I ask you, what's the net force acting on that object? Well, first of all, let's think vertically and horizontally here. So we have a vertical downward force of 20 and a vertical upward force of 20. Those two cancel each other out. They're opposite forces in opposite directions. Now let's think horizontally. So we have 40 going to the right and 30 going to the left. So this 30 cancels out 30 of this 40 because they're in opposite directions, leaving behind only 10 newtons to the right. That force, the force that's not canceled out by anything else, that is, in this case, our net force. Force is a vector, so 10 newtons is not enough. We need to say 10 newtons to the right or 10 newtons with an arrow. We need a magnitude and a direction. Again, forces are vector quantities. You need both. All right, Newton's third law, we'll deal with it more later in this unit, but you guys know that Newton's third law is for every action, there's an equal and opposite reaction. You can't push on something without being pushed back on by that object. And we'll see that in some of our practice problems here in just a few minutes. All right, we're not going to spend much time on this slide, but you will see mentioned in AP Physics 1 inertial mass and gravitational mass. Don't let those terms confuse you. They actually measure the same thing, an object's mass in kilograms. To calculate the mass using an inertial mass, you're going to take an object of unknown mass. Well, first of all, let's think about Newton's second law for a second. Let's solve that for mass. So that would be m equals F net over A. So if we have an object of unknown mass and we apply a known force and we measure an acceleration, divide that out, the known force divided by the measured acceleration, that will give us the object's inertial mass. So inertial mass, apply a force to an unknown mass, measure its acceleration, calculate mass going F net equals, or m equals F net over A. That mass is your inertial mass. Now, gravitational mass is calculated using the law of universal gravitation. So we could measure the gravitational force between two objects, one of known mass. This is the distance between their centers. This is the universal gravitation constant. It's always the same. And we could use this formula to calculate the unknown mass. Another way of going about the same thing is taking a balance and putting a known mass on one side, an unknown mass on the other, and continuing to either add or subtract known mass until it balances out. That's the gravitational mass. Turns out that gravitational mass and inertial mass are the same. They measure the same thing. They're equivalent to each other. And this is one of the reasons why that two masses will fall at the same rate on Earth. All right, let's talk a little bit more about forces. Remember that mass is not a force. Mass measures how much matter is in an object. Your mass is the same no matter where you're at in the universe. You're made of the same amount of atoms. Weight, on the other hand, is a measure of force. Weight is a force. It's a measure of the gravitational force on an object's mass. More mass means more weight. So it turns out that weight is equal to an object's mass times the acceleration due to gravity. Weight equals mg. Weight is a measure of gravitational force. Also in this unit, we're going to differentiate between contact forces and non-contact forces, or field forces. So a contact force is a force that's applied by objects that actually touch each other. We're going to talk mainly about three contact forces in this course. Frictional force, which we'll talk a lot more about next week in the week 6 review. But we know that frictional force happens between surfaces, and frictional force always acts in the opposite direction of motion. We might also lump in air drag as a type of frictional force. The normal force, that's the support force exerted on an object that's in contact with a fixed object. So for example, if we had a box sitting on the ground, let's say we know that that box weighs 40 newtons. So its weight is acting down. Well, if there wasn't an upward force acting on that box would accelerate downward because there would be a net downward force acting on it. We know that doesn't happen because if the box pushes down with a gravitational force of 40 newtons, there's a force coming up from the ground that's also 40 newtons. That force, that support force, is called the normal force. And on a flat ground, it's typically equal and opposite to the gravitational force or the weight. We'll talk a lot more about normal forces in the next couple of weeks. And then we'll talk about an applied force. So this is when an object is just being pushed on or pulled on by something. So maybe you've got a rope attached to a box and you're pulling it. Or maybe you go to one side of the box and you put your hands on the box and you push on the box. Or maybe you put your hands around the bottom of the box and you lift upward on the box. Those are applied forces. All three of those are contact forces. We'll also deal with non-contact forces, though. So these are when forces are applied by an object that's not actually touching the other object. Sometimes we call these field forces. They act across distance. The one that we'll deal with the most in this course is gravity. We'll also deal some with the electromagnetic force of attraction between charged particles. And not so much in this course, but if you go into AP Physics 2, or maybe even AP Chemistry, you'll talk about some of the forces in the nucleus that actually hold that nucleus together. Turns out these are really, really strong forces, but they only act over very short distances. The two to think about in this course are these two, gravity and the electromagnetic force. All right, so the big idea in this unit, and really the most important idea in this unit, net forces cause motion, and maybe even better, net forces cause acceleration, changes in motion. Whenever there's a net force, there is acceleration. That is F net equals ma. And sometimes you'll see that instead of seeing it written this way, sometimes you'll see it written like this, where that's the sigma symbol, the summation symbol. So that's the summation of all the forces acting on an object equals ma. These mean the same thing. Net force equals mass times acceleration. Another really big idea in this unit are free body diagrams. So these are diagrams that are used to show the relative magnitude and the direction of all the forces that act on an object. You typically don't show components of forces in these diagrams. You guys haven't dealt with components very much yet. You will later in this unit, but you do not show components on free body diagrams. So let's look at an example. So here's an example of an object, and we're going to think of this object as essentially like a dot, and we're going to draw in all the forces that act on that object. So if we go back to the prompt on the previous slide, so it tells us here, free body diagrams may be depicted in one of two ways. One in which the forces exerted on an object are represented as arrows pointing outward from the dot, and the other in which the forces are specifically drawn at the point on the object at which each force is exerted. We have both examples in the next slide. This is the example we're going to use the most in this course. So think of the object as like a dot or a box, and then you're going to draw in each force that acts on that object. So let's just say this is like a box sitting on a table. So we have the gravity force acting downward. So we draw that arrow down from the center. We have a normal force from the surface pushing up. That's equal and opposite to the force of gravity. So we're going to draw these two arrows at about the same length, but we're going to show that the normal force is acting upward and the gravitational force is acting downward. In this case, we also have an applied force that's pushing or pulling rather the box. So that's this arrow. And then we have a frictional force that always acts in the opposite direction of motion. Now it looks to me like the blue arrow is a little bit longer than the red arrow. That's telling me that we have a net force acting to the right, which means that this box is going to accelerate to the right because there's a net horizontal force pulling it to the right. So this is the type of free body diagram that we're going to use most often in AP Physics 1. Every now and then you'll be asked to draw one like this, where you draw the forces at the point on which those forces act. So let's say in this case, we have this box, and the box is being pushed. It's being pushed from the left toward the right. So this force, I'd like to show these as F sub A, meaning applied force. Well, friction, which is this force, friction acts at the surface. So it acts where the box meets the ground. So it's showing you here that this is the frictional force, and it's acting opposite of motion. It's acting toward the left. And then also at the surface, the weight is pushing the box against the ground, so downward, and the normal force is pushing up on the box from the ground up toward the box. So either one of these types of free body diagrams are acceptable. This is the type that I want you to focus on most often. That being said, let's look at a couple of examples. So a box sits on a flat horizontal surface when it is pulled with a horizontal force to the right. It accelerates. A frictional force also acts on the object. Draw a free body diagram for the box. So we're going to draw a box like so. I like to come to a middle point in the box. So we know that it's sitting on this table. We know that it has a gravity force acting downward. I usually like to draw my gravity force and is F sub G. You could draw it in as weight. That would work too. We know that it's sitting on a table, which means there's a normal force. And that normal force is equal but opposite to the weight. I'm going to write that as F sub N. And those two arrows, the up and down arrow, should be the same length, opposite directions. So we also have an applied force to the right. So we're going to draw that in like so. And I'm going to write that as F sub A, applied force. We have a frictional force. Well, remember that frictional forces always act in the opposite direction of the motion. So if the box is being pulled to the right, the frictional force acts to the left. I'm going to write that as F sub F, frictional force. Now it tells us that this box accelerates. That means it's got a net force acting on it, which means that this force, the applied force, is bigger in magnitude than the frictional force. So notice I drew my applied force arrow longer than my frictional force arrow. That just lets me know there's a net force to the right acting on this box. These free body diagrams are going to be really important to help you go in and work problems. First of all, before you can work most of these problems, you're going to have to determine where the net force is, which direction it acts, and so on. So these are an important tool for helping you to do that. Here's another example of a free body diagram. So they're wanting us to draw a free body diagram for box M1 and box M2. This setup, where you have a box on a table with a pulley and a rope connected to another box, this kind of setup is really famous in physics classes. It's called a modified Atwood machine. And I'm sure you're going to see that terminology as you go through this unit and upcoming units in the course. So to draw the free body diagrams for the two boxes, let's just draw the boxes first of all. So this is going to be box M1 and this is box M2. So you essentially remove the objects from their environment and then just draw the forces acting on them. Let's first of all assume in this particular example that there's no friction, that this is a frictionless table. Maybe it's been greased or something. There's no friction in the pulley. That's a fairly common assumption in lots of physics problems. So let's assume there's no frictional force. So if that's the case for box M1, we have its weight acting down. We'll label that as F sub G. It's on a table, so it's being supported. Therefore, there's a normal force pushing up on it. And that normal force is the same magnitude as the weight. So we draw these two arrows, the up and down arrows, about the same magnitude. And then it's connected by that rope. So there's some force pulling it to the right. And we could label that force as tension. That's the force in the rope. Or we could label that as F sub A, applied force. Either one works. I think those are all the forces acting on box M1. And that tells us that the net force acting on this box is whatever the magnitude of that tension is. So the net force is the tension force acting toward the right. Now for box M2, we've got the weight of that box acting down, Fg. And then we've still got a force in that rope acting up. That tension here is the same as this tension here. This box, we're not sure. We're not told the box is accelerating. More than likely, this box is going to start to fall, right? If that is true, if that box is falling, that means that this force, Fg, is bigger than that tension force. So in that case, there would be a net force acting in the downward direction. All right, any questions on free body diagram so far? All right, let's get to some problems then. So in this problem, we have two boxes. The blue box, mass A, has a mass of 4 kilograms. And the red box, mass B, has a mass of 10 kilograms. So it says if a force of 80 newtons is applied to the right on box A, so we start to push on box A with a force of 80 newtons. What is the acceleration of the system? Assume there's no friction. So if we push on that box of 80 newtons, vertically, we've got the weights acting downward of both boxes, and we have a normal force acting upward on both boxes. So vertically, there's no net force. Well, there's no frictional force in this case, which means the only horizontal force is this 80 Newton force. So the net force is 80 newtons. Now that net force doesn't just act on the 4 kilogram object, because the 4 kilogram object is against the 10 kilogram object. That 80 newtons acts on the whole system. So we're going to say that the acceleration equals F net over m. That's just Newton's second law. F net equals ma, soft for acceleration. And we're going to take the net force acting on the system, 80 newtons, And we're going to divide that by the whole system mass, which would be 14 kilograms. And we end up with an acceleration of 5.71 meters per second square. And that's positive 5.71, which means 5.71 meters per second squared to the right. So answer A looks good. That's the acceleration of not only box A, but it's also acceleration of box B. It's the acceleration of the whole system. Anyone have questions on problem 1? All right, here's problem 2. Same setup, still applying a force of 80 newtons to the right on box A. What force does box B apply on box A? So here's what we got to think about. We're pushing on A with a force of 80 newtons. That 80 newtons is acting on the whole system, and it's causing the whole system to accelerate at 5.71 meters per second square to the right. Which means there's a net force acting on box B. Let's just think about box B now. Let's don't think about the whole system. Let's just think about box B. If we want to know the net force acting on box B, let's think about Newton's second law. So this is just box B. The mass of box B is 10 kilograms. The acceleration of box B is 5.71 meters per second square. That means that the net force acting on box B is 57.1 newtons to the right. Now, is that what problem 2 is asking us? It says, what force does box B apply on box A? That's not what this question is asking us, because you got to think about what's applying the net force to box B. And the object that's applying the net force to box B is box A. So this is the force of box A on box B, 57.1 newtons to the right. But now you've got to think about Newton's third law. If box A pushes to the right with 57.1 newtons on box B pushes equal but opposite to that on box A. So if A pushes B to the right 57.1, B pushes A to the left at 57.1. That's our answer. Now, another way we could think about this problem is, let's just think about box A for a second. So if we're only thinking about box A, let's calculate the net force acting on box A. Box A has a mass of 4 kilograms. It's accelerating at 5.71 meters per second square to the right. So let's go 4 times 5.71, and that gives us 22.84. Now, how can that be? How can there only be a net force of 22.84 newtons to the right acting on box A? Because we're pushing on box A with a force of 80 newtons. Well, the way that works, if we go 80 minus 22.84, we end up with essentially 57.1. 57.16. So we've got some rounding issues. So here's the deal. Even though we're pushing with a force of, and let's draw a free body diagram for A. It might be the easiest way to do this. So here's object A. We know that its weight is acting down, F sub G. Normal force acting up, F sub N. Those cancel out. There's a force pushing this box to the right of 80 newtons. So we'll say FA equals 80 newtons. But we now know there's a net force of 4 times 5.71. So there's a net force of 22.84 on this object. Well, that means there's got to be a force acting this way. And that force is the force of box B pushing back on box A. And the magnitude of that force has to be the total force, 80 newtons, minus the net force acting on box A, which was 22.84. And that comes out to be 57.1 newtons to the left. So two different ways to work that problem, both with the same solution. Problem 3 is going to look very similar. So this one wants to know what force does box A apply on box B. So we really already worked this problem. We worked it by taking just box B, draw a free body diagram. So we've got weight acting down, normal force acting up. We've got a force of box. This is the force of box A on B. That force is the net force acting on box B. So we can calculate it by using Newton's second law. In this case, take only the mass of box B, 10 kilograms, multiply it by the acceleration of box B, 5.71 meters per second square, and end up with a net force of 57.1 newtons. And box A is pushing box B to the right. So our answer here would be B. All right, anyone have questions on problem 2 or 3? Because those can be a little confusing. All right, so here's 4. So we have a 50-kilogram parachutist falling through the air. 350 newtons of drag force act upward on the parachutist. How much net force acts on the parachutist? So we're just going to draw the parachutist here as a box, so we can do a free body diagram. There's a weight force acting down, and in this case, there's a drag force acting up. We know that the drag force is 350 newtons. Drag force is the type of friction. It always acts opposite of motion. So if the guy's falling down, the drag force acts up. Now, some of you are going to be quick, and you're going to put 50 kilograms right here. 50 kilograms measures mass, not weight, not force. So to put in the force of gravity, we need to convert this mass into a weight. Remember that weight equals mg. So we're going to go 50 kilograms times the acceleration due to gravity, 10 meters per second square. And we're going to end up with a weight or a force of gravity here of 500 newtons. We don't have any horizontal forces in this particular problem. So to find our net force, let's just take the 500 down and add it to the 350 up. So we could say negative 500, because remember, negative means down, plus positive 350, and we end up with a net force of negative 150 newtons. Or negative means down, so 150 newtons down. Key to this problem is remembering that kilograms measure mass, not force. To use that, you've got to convert the kilograms to weight, convert to newtons, and then calculate the net force. So now we want to know what's the acceleration of the parachutist. Well, in the previous problem, we found the net force to be 150 newtons down. We know the mass of the parachutist is 50 kilograms. So let's use Newton's second law. And let's take the net force, negative 150. Let's divide it by the mass, 50. And we'll end up with an acceleration of negative 3 meters per second square, or 3 meters per second squared down. And you can write that either way. You could write negative 3 meters per second squared, or you could write 3 meters per second down. Both are correct answers. Both show magnitude and direction. All right, so now we have a bucket, a 10-kilogram bucket suspended from a rope and held without moving. how much tension is in the rope. So again, we're just going to draw the bucket as a square, a box, and think about a free body diagram here. Let's remove the rope. So we know there's a weight acting on that box, Fg, and we know there's a rope. We know that rope's pulling up. And typically when we have ropes, the force in the rope we call the tension force. Now in this case, the rope isn't moving. Well, that tells us the box rather isn't moving, the bucket isn't moving. Well, that tells us there's no net force, which means if we only have a force acting down, we must have a force acting up that's of equal but opposite magnitude. So the force of gravity is the weight of the bucket. Again, some of you are going to be quick to put 10 kilograms here. Remember, that's not a force, that's a mass. So we have to, again, to go to weight equals mg, and we're going to take 10 kilograms for the mass, and then g is 10 meters per second square. And we end up with a weight, force of gravity of 100 newtons acting down. Well, if there's 100 newtons acting down, and this bucket isn't moving or isn't accelerating, there must also be 100 newtons of force acting up. The only thing that could apply that force is the tension. So in this case, 100 newtons is the tension, and that's acting in the upward direction. All right, any questions on problem 6? All right, so here's problem 7. So this one's a bit tricky if you haven't worked these kinds of problems before. So now we have the same bucket still attached to a rope. The bucket is being lifted at a constant velocity. What is the tension in the rope? Keywords, constant velocity, which means 0 acceleration. Since there's 0 acceleration, that means there's 0 net force, which means if we draw a free body diagram, the weight acting down still has to be balanced out and equal to the force of tension in that rope. So if the weight acting down is 100, the tension in that rope still has to be 100. That circled phrase is crucially important, constant velocity. Constant velocity means no acceleration. No acceleration means no net force. So our answer here, 100 newtons, and that's acting in the upward direction. All right, here's one more take on that problem. So now we have same bucket. This time the bucket is accelerating, and it's accelerating upward. So we're accelerating the bucket up. So we have Fg acting down. We have where the bucket's accelerating up, which means there's got to be a net force in the upward direction. So I'm going to draw this arrow longer than the gravity arrow. This is my tension. And I can calculate how much tension by, first of all, calculating the net force. And I'm hoping from this free body diagram, you see that the net force has to be the difference in, well, it has to be the tension plus the gravity. So the tension force is what we're looking for. We don't know what that is. The gravity force is negative 100 newtons. And that negative is important for this problem. This is negative 100 newtons. We don't know what the tension is. That's what we're looking for. The net force we can calculate. The net force is MA. So mass of 10 kilograms times acceleration of 2 meters per second square. We end up with a net force of 20, positive 20 meters per second square. So now we can solve, I'm sorry, net force is not meters per second square. Net force is 20 newtons. So now we can solve for tension by just solving this equation right here for T. So we've got to add 100 newtons to both sides. And when we do, we end up with a tension of positive 120 newtons, which would be answer B. So use your free body diagram. Remember to use the signs in your equations to represent direction. And then F net remember, is just another way of saying the sum of all the forces acting on the object. Any questions on problem 8? All right, so again, same problem. This time we're accelerating in the opposite direction. So this time we've got weight acting down. We know we've got tension acting up, but in this case, the tension's got to be smaller in magnitude because the net force is downward. We're accelerating in the downward direction. So same idea, net force equals the summation of all the forces acting on the object, which is the tension force plus the gravitation force. So the net force, we again can calculate. F net equals MA. So 10 kilograms times -2, 2 down, would give us a net force of -20 newtons. We're looking for tension. And the force of gravity is the weight, which is 10 kilograms of mass times 10 meters per second square, G. So that's -100 newtons, 100 newtons down. Add the 100 to both sides to solve for T. So T is going to end up being positive 80 newtons. Answer choice D. Key idea, net force is the sum of all the forces acting on the objects. When you're summing them, you have to remember the signs. Negative down, positive up. Negative to the left, positive to the right. That's crucial when you're working with free body diagrams and this kind of scenario. All right, so now we go back to this modified Atwood machine. And it tells us that this Atwood machine has a 10 kilogram box, M1, so this is 10 kilograms, connected via a massless rope and a frictionless pulley to a 5 kilogram box. It's 5 kilograms. What is the acceleration of the 5 kilogram mass when it's released? So there's no friction. The easiest way to work a problem like this is, first of all, calculate the acceleration of the system. And here's what we've got to think about. If there's no friction, then the net force acting on this system is going to be the weight of that object right there. So let's calculate the weight of that object. Mass of 5 kilograms times acceleration due to gravity of 10 meters per second square. The net force acting on the system is 50 newtons. Now to calculate the system acceleration of the system is equal to the net force acting on the system divided by the mass of the system. Net force acting on the system is 50 newtons. The mass of the system is 5 here plus 10 there. All the mass in the system, 15 kilograms. We divide that out, and we end up with a system acceleration of 3.33 meters per second square. Now, since these objects are connected by a rope, they all accelerate at the same rate. Now, in this question specifically asks about box M2. We know it's going to accelerate down. So its acceleration is negative 3.33 meters per second square, or 3.33 meters per second squared down. If we had the same question, but we asked for the acceleration of box M1, it would be 3.33 meters per second square to the right. All right, so the last thing we're going to look at here, problem 11, it's asking us for how much tension is there in this rope. Well, we already calculated in the previous problem that the acceleration of both objects is 3.33 meters per second square. So to find the tension in the rope, let's do this. Let's draw a free body diagram for either. We could do the free body diagram for either M1 or M2. I'm going to do it for M1. So we've got a force of gravity acting downward. We've got a normal force acting upward. And then we have this tension force acting to the right. And what I hope you realize is this force of gravity and this normal force, they cancel each other out, which means the net force acting on box M1 is the tension. The tension in the rope, the pull in the rope is the net force acting on box M1. We know when we're dealing with net forces, this is our equation. This net force is equal to the tension on box M1. So let's calculate it. Let's put in the mass of box M1, 10 kilograms, times the acceleration of box M1, 3.33 meters per second square. Calculate that out, and we end up with a net force on box M1 of 33.3 newtons. And in this case, that would be to the right. That is our net force on box M1. That is our tension in the rope. Now, we could calculate this another way from the other box's point of view. So now let's just think about box M2. So we're going to get the same answer going about it a different way. Let's draw a free body diagram for box M2. We've got FG acting down, and we have the tension in the rope pulling that box up. We know the net force acting on that box is going to be the sum of the forces acting on that object, Fg plus tension. The net force acting on that object is equal to ma for that object. So the mass of that object is 5 kilograms. We already know it's accelerating at 3.33 meters per second square. So multiply that out. So we end up with a net force of, let's just write it in here, of 16.65. And we know that's downward. So that's negative 16.65. I should have had a negative right there because this box is going to be falling down. That's equal to the force of gravity. Well, the force of gravity acting on this box is its weight. Its weight is its mass, 5, times the acceleration due to gravity, negative 10 meters per second square. So this is negative 50 newtons plus T. We solve that out for T by adding 50 to both sides. And that ends up with a net force of 33.35. So we got a little rounding error in there, but that essentially gives us positive 33.35 newtons, or 33.3 newtons up. So either way, we can calculate tension by calculating from the perspective of this box or from the perspective of that box. Start with a free body diagram. Use that free body diagram and the net force to solve for tension. Got one more problem I want us to look at, and this is a true Atwood machine. So a true Atwood machine has no table involved. It's just two masses strung over a pulley connected by a rope. So mass M1 is 20 kilograms and mass M2 is 60 kilograms. Well, let's assume that right now someone's holding each mass in their hands. There's no friction between the pulley and the rope, no drag. We want to know what's the acceleration of box M1 when the boxes are released. Just like we did in the modified machine, Atwood machine problem, we need to first of all calculate the acceleration of the system acceleration. And to do that, we first of all need to figure out what's the net force acting on the system. So over here, we're going to have 60 kilograms, which is 600 newtons of weight, right? Multiply that 60 by 10 meters per second square. And over here, we're going to have 200 newtons. 20 times 10 meters per second square. What I'm hoping that you see is that over here, let's just do a free body diagram for box M2. For box M2, we've got 600 going this way. Well, that pulley causes that 200 to pull up. So we end up with a net force on box 2 of 400 newtons. Same for box M1. What I'm getting at is that the net force acting on this system is the 600 minus the 200. 400 newtons of net force act on this system. Calculate the acceleration of the system. We're going to say A equals F net over M. We're going to take the net force acting on the system of 400 newtons. We're going to divide that by the total mass of the system, 80 kilograms, 60 plus 20. And we're going to end up with an acceleration of 5 meters per second square. Now, in this case, since we're asking about box M1, that box is going to be getting pulled up, right? Because M2 is heavier. So that would be 5 meters per second squared up, or positive 5 meters per second square. All right, again, key idea in this unit, F net equals MA. Most important idea in all of Physics 1. Remember that you can also think of it as the sum of the forces acting on an object equals MA. When you're summing those forces, it's really important to use positives and negatives to indicate direction. Positive means to the right or up. Negative means to the left or down. If you follow that simple rule and you use your free body diagrams, you ought to be able to work all of the problems, at least in the beginning of the dynamics unit. Any questions I can answer for you guys? All right, we're going to get into deeper, more detailed problems next time. We may even work with some problems that act in more than one dimension. So I hope to see you guys next Friday at 10 a.m. Be sure to check out the A+ College Ready Science YouTube channel. Thanks for being here. Bye-bye.